Okay. Hi, everyone. My name is Suren Shams. I have a PhD in rock mechanical engineer from University of Sherbrooke, and currently I'm working as a geotechnical engineer, rock mechanical specialist in Hatch, and I'm a lecturer of applied rock mechanical course in University of Sherbrooke. I'm happy and thank you for being here. I'm happy to present a little about my research I did back down in my PhD degree. And today I'm going to talk about a little about the understanding of tensile failure in geomaterials, especially in macro scale. And because we know always the macroscopic failure, what we see in the field in the rock engineering project, we see the visible final fracture, but we don't know the process and how it begins. Today, I'm going to talk about this macro scale process a little, especially on the tensile loading, and what's the importance of tensile fracture. And let me okay. We're going to begin with the importance of
Did you stop sharing your screen there, sir?
Yeah, you have my screen?
No, I don't see it anymore.
Okay. Do you have my
Yep.
screen?
Yep.
Okay.
It's back on.
Yeah. Okay. The first thing that we're going to talk, actually, the whole thing we're going to talk is the importance of tensile strength in practice, engineering practice. Before we dive into that tensile testing, tensile fracturing, tensile strength of materials, it's important to ground ourselves in why this topic matters so much in day-to-day geotechnical practice in rock mechanical engineering. Whenever a rock structure fails, whether it's a tunnel crown, a slope, or a rock concrete interface, we immediately see the consequences. It could be safety hazards. It could be damage to infrastructures and costly interruption to our services or operations. But what's less visible and far more important to us as engineers is how these failures start. Because as I said, we see only the final visible fracture or failure. Almost every catastrophic rock failure begins the same way, with the initiation of microcracks and propagation growth of microcracks. As these microcracks accumulate, they result in a macroscopic fracture that ultimately they control the stability and instability of rock structures. But the important point here is that rocks are inherently much weaker in tension than in shear or in compression. So even relatively small amounts of tensile stress can trigger the first microcracks. These microcracks accumulate and result or cause the final failure. That means what? That means that tensile strength is not only a simple material property like other properties of rocks. It's a property or a key parameter that controls or governs the onset of failure. Therefore, if we have a reliable it's critical to have a reliable understanding of tensile failure or tensile strength of materials. And here are a few examples of what tensile failure looks like in the field. On the surface, we often think these failures are dominated by, I don't know, by gravity or by shear movement. But in reality, the very first stage of these events is almost always tensile cracking. Therefore, the tensile cracking or tensile strength of materials or rocks or other materials are very critical and crucial. And these are another very, very important examples of the tensile failure. Spalling in and rock bursts in deep mining. When we have a high stress concentration, these type of failures are pure tensile failure. Then here the tensile strength, having a reliable, very good estimation of tensile strength of materials to model these rock fractures or rock bursts on spalling is very, very important. And the tensile strength and tensile fracturing behavior are also critical parameters for structures between rock concrete structures or interface between rock and concrete. As you can see, it controls the overturning resistance in dam foundation, and it can be very important, the tensile strength between the shotcrete and the rock wall of the tunnels or the concrete liner that controls the stability of the whole system. But the question is that, do we really know the true tensile strength of a rock? And to answer this, we have to go to the practice. So naturally, we rely on laboratory tests to quantify or determine the tensile strength of materials. In practice, we mostly depend on these two tests, these two testing methods, direct tensile test and indirect or Brazilian tensile testing, or we call it sometimes Brazilian splitting tensile test. These are two common tests that we do in laboratory, and they are based on the ASTM standards and ISRM recommendation. But the first one, the left side, direct tensile test, is reported to give the true tensile strength of material, but technically they are problematic and they are difficult to run in laboratory. So that's why we mostly depend on the right side test, Brazilian tensile test, to determine the tensile strength of material, because it's simpler and easier to run this test. But the question is that the problem is, the issue is that these two methods don't produce the same tensile strength values for different materials. According to many research and studies that we have seen that Brazilian tensile strength overestimates direct tensile strength. For example, this is a graph based on different studies from Pratt and Dietrich that shows Brazilian tensile strength for metamorphic, igneous, and sedimentary rocks overestimate the direct tensile strength. Yes, we know this up to here, but we don't know why. It's the question that I try to answer. How we can this difference between tensile strength obtained from direct tensile test and Brazilian tensile test, how we can explain it, especially from a macro scale point of view. This is the core question of my research. To answer this question, we developed a methodology, experimental methodology. This is the general approach and methodology that we had. We ran many tests on Brazilian and direct tensile tests, two different tests. And we had the materials, granite and mortar. As you can see, the specimen shape, we have circular disc and rectangular prismatic for the Brazilian test and direct tensile test. And we ran our test on intact materials and biomaterials, intact granite, intact mortar, and rock concrete, rock mortar biomaterials. And most importantly, to monitor the fraction process during the loading, we use the two advanced monitoring system, acoustic emission system, that we can say we can hear the microcracking inside the material, and digital image correlation technique that we can visualize the strength concentration or deformation over the surface of materials. This is the I like this figure. This is a figure to explain the acoustic emission microcracking monitoring that I produced this one by ChatGPT. I like this one. Yeah. And if I want to explain this, how we monitor the microcracking fracture or fracture evolution during the loading process using acoustic emission is that as the specimen is loaded under compression, tension, or bending, shear, whatever the load is, the internal damage progressively accumulates. Before we observe that final visible fracture, as we can see here in laboratory, we see a laboratory, there are like distributed microcracks inside the material. These microcracks are release strain energy that propagate as stress waves inside the material. This, as you can see, this stress wave orange one is a like microcrack that is produced released energy. This energy or stress waves is detected by acoustic emission sensor that attach on the surface of a specimen. This stress wave is converted to like an electrical voltage signal and is sent to data acquisition system. Therefore, before these two, the acoustic emission sensor and the data acquisition system, we have a like signal processing chain that is composed of pre-amplifier, filter, amplifier, to process and to treat the signals to be detectable and to reduce the noise inside the signals. When the data acquisition system detects these nodes, these signals, it monitor here like a digital wave, as you can see. Each spike or each waveform here, it's equivalent or correspond to a microcrack inside the specimen. Okay, up to here, we have a general information that how we can hear and visualize that microcracking inside the specimen far before what we arrive the final failure. But the more important things about the acoustic emission monitoring is that using this system, this technique, we can do obtain three important information. First one is crack initiation time. Actually, we can determine the temporal distribution of microcracks. We can know when exactly the microcracks started to produce inside the rock. It could be the laboratory sample, or it could be a large scale sample. And we can detect the crack location. Actually, we can localize the microcracks inside the specimen. That's very important. We know where and when it started, fracturing or microcracking started. And more importantly, this is very important in my research, is that we use this acoustic emission to determine the crack mechanism. Actually, as we have in large scale, we have shear microcrack, we have tensile microcrack, we have shear cracks or fracture, tensile fracture, compaction fracture. This story is the same in micro scale. We have tensile crack, shear crack, and compaction cracks. Therefore, we use this acoustic emission or AED system or technique to determine the type of microcracks. Actually, I'm emphasizing on this because it is very important. I use this technique to determine the type of cracks that we use to explain why the direct tensile strength is different from the Brazilian tensile strength. And here is I'm not going to explain this complex mathematical formulation. Here is just to say that we use the moment tensor inversion method to determine the type of microcracks. The moment tensor inversion has 6 independent components. We need to determine 6 components. For determining these 6 components, we need at least 6 acoustic emission sensors to attach over the surface of a specimen. When these sensors detect a signal or a microcrack at 6 sensors, using the first motion amplitude and the arrival time of the p-wave, we can determine these parameters based on MESO, MDC, MCLVD that I'm not talking about them, but using these and this criterion, we can determine that if the crack that has happened inside the model is a shear crack, is a compaction crack, is a tensile crack. Therefore, we use moment tensor inversion to determine the type of microcrack inside the specimen. The second monitoring system that we use is DIC or digital image correlation technique. That is simply high speed, high resolution camera that we can take the photo from the surface of the sample during the loading process by different frame, different rates. As I remember that the frame that we could take the photos between 60 frames per minute to 1,000 frames per minute. If I want to explain the technique or how we determine the deformation, is that first we need to produce, as you can see here, the speckle pattern. These black dots over the white column. It's called speckle pattern. We need them to track the deformation. When we choose the region of interest that we want to determine the deformation, the software comes and divide this surface to a small subset of pixels. That's like this blue subset. And during the loading process, this subset is tracked by the software, and each displacement and the deformation between this original subset before loading and the subset or the same subset, corresponding subset on the surface of a deformed specimen during the loading, and comparing these two subsets at each loading step, we can determine the displacement and deformation. And finally, we can map the whole deformation or strain localization over the surface of a specimen. As you can see in the monitor here, is a like a typical way that we visualize the strain over the surface of a specimen. So, while acoustic emission tells us when and how microcracks start from form internally from the inside the specimen, DIC tells us where deformation localized on the surface of a specimen. Together, they allow us to link microscale cracking to macroscopic fracture and deformation. Here, I'm going to talk a little, just short, about the material and specimen preparation that we use during our experimental campaign. We had two materials, mortar and granite. Mortar as a fine grain material and granite as a coarse grain material. We had two different shapes, circular disc and prismatic, rectangular prismatic specimen. We had different intact rock, intact mortar, intact granite, and biomaterial granite mortar. And this is the process of the material or specimen preparation that I'm not talking about. And this is some samples of direct tensile test we prepare. And this is a sample for direct tensile test and Brazilian tensile test. And you can see the speckle pattern over the surface that it's needed to be used for the DIC or digital image correlation technique. And this is the acoustic imaging sensor attached over the surface of the Brazilian specimen. And this is an overview of some of samples that we prepared and tested. Over 100 specimens were tested in this experimental program. And here you have our loading system, acoustic imaging system, and digital imaging correlation system, including the camera, the light source, and data acquisition system. And here again, you have the direct tensile test specimen, Brazilian specimen with the acoustic emission sensors mounted on the surface of a specimen and the speckle pattern on both samples. And this is a 3D illustration of how we attach the configuration of acoustic emission sensors over the surface of a specimen. We use 8 sensors for direct tensile test and 10 sensors for Brazilian test. And again, I repeat that we need at least 6 sensors to be able to use moment tensor inversion to detect or determine the type of microcracks. From now on, I will talk a little about the results. First, let's have a look at very classic result. Direct tensile strengths obtained from direct tensile test and tensile strengths of granite obtained from Brazilian test. Here is like the result of 4 samples as an example for direct tensile test and 6 samples for Brazilian test. As you can see in the first view, we have higher tensile strength as a bar chart in Brazilian test than direct tensile test. Here, just to help you understand a little better, DG is Brazilian granite, DG is direct granite. As you can see here, like other studies, we showed that Brazilian tensile test overestimate the tensile strength obtained from direct tensile test. Therefore, the direct tensile test strength is 70% of that obtained from Brazilian test. This is in the same range from the literature or other studies. And we know it, up to here we know it. Other researchers has shown that this ratio between direct tensile strength and Brazilian tensile strength. But why? Here I try to explain the reason. On the left side panel here, you have one Brazilian specimen and one direct tensile specimen. The Brazilian fixed taper shows a microcrack detected by acoustic emission. And the size and color of cracks show the amplitude or energy or magnitude of the microcracks. The bigger or the more red microcracks means that they produce higher energy. They are stronger. Keep it in mind. They are stronger. On here, on the left side, we have the composition or components of microcracks. We determine the type of microcracks. For Brazilian test, you see here we have 20% tensile, but we have 50% shear. Sorry. But in direct tensile test, therefore, we have majority of microcracks in Brazilian test as shear. But in Brazilian direct tensile test, we have 63% tensile and only 70% shear. Therefore, in direct tensile test, we have predominantly tensile microcracks. This is just to show that the consistency between results. This is we had a lot of specimen, but this is just only for results for Brazilian disc specimen. As you can see, in all of the cases, we have the majority of microcracks as shear microcracks. Therefore, we can say that the Brazilian tests are shear microcrack dominated. And on average, we have 50% shear and only 28% tensile microcracks. But what about the direct tensile test? This is again 4 samples from direct tensile test. As you can see here, we have the majority of, on average, the majority of microcracks as tensile, 55%, and only 22% are shear. If I compare both Brazilian granite and direct granite specimen, and you see on the left side, we have the majority tensile microcracks during the direct tensile test loading. And we have the majority of microcracks inside the Brazilian disc as shear. That could explain the effect, why we have different tensile value, tensile strength value from direct tensile test and Brazilian test. Keep this in mind that we have more tensile microcracks in direct tensile test, and we have more shear microcracks in Brazilian test. We will come back to that. To verify this, to confirm this, we evaluated or studied the deformation and strain types over the surface of the same specimen. This is 2 specimens, the DIC photos from just 1 frame before the final failure. As you can see that it shows the stress concentration over the surface of a specimen. On the left side, we have direct tensile test. On the right side, we have Brazilian test. We try to quantify and distinguish between, to determine how much of this deformation of strain over the surface of specimens, how much is Brazilian, how much is shear strain, how much is tensile strain. Here we have a histogram distribution of the type of strain. I'm not talking about this because it's a little complex to explain that, but I want to highlight the right side bar chart. This bar chart shows the shear to tensile ratio on microcracks. The deformation strain, shear strain over tensile strain ratio. In direct tensile test, we have less than 1, about 0.8 for this ratio. It means that the most of the strain or deformation on the surface of a specimen were detected as tensile. But in contrast, in Brazilian test, as you can see here, this ratio shear to tensile is about 1.5. It means that we have 1.5 times more shear deformation shear strain than tensile strain. Therefore, again, from the DIC result, we could confirm that what we obtained from AE data. The direct tensile test is tensile microcrack, tensile strain dominated, but Brazilian tests are shear microcrack dominated, or shear strain dominated, or shear deformation dominated. We see here again, this is the result of DIC, and these are the result of microcracks, acoustic emission. we have mostly shear deformation in Brazilian, and we have mostly shear microcracks in Brazilian. We have here mostly tensile microcracks or tensile deformation in direct tensile test. And the same, we have here majority of the data or microcracks are tensile in direct tensile test. Therefore, we can conclude that higher proportion of microcracks as shear microcrack can result in higher tensile stress of Brazilian disc. In contrast, in other words, when we have a smaller proportion of shear microcracks in their tensile test, we have a smaller overall tensile stress. It's what we concluded, but let's explain a little more. It's related to the loading configuration. This figure illustrated simplified schematic representation of loading configuration for Brazilian test and direct tensile test. In Brazilian loading, we apply compressive loads on both sides of the specimen, or just one side and the other side is fixed. And in result of the applying that compression, we induce like tensile load in horizontal direction. Therefore, we have compression, we have tension induced load. But in direct tensile test, we apply direct tensile loads that we have mostly tensile loads or between grains or inside the grains. Therefore, we can say that in these two different configurations, we have the resultant normal stress over microcracks as compressive in granite in Brazilian disc. They are the normal load, as I showed here in simple form as the black arrow. These normal loads are compressive compression, but these normal loads are tensile inside the specimen for direct tensile test. We can say that this macro sliding is more difficult in Brazilian because we have no compressive normal load, and it takes time, it takes energy to shear the specimen, and shear the microcracks inside the specimen, inside the Brazilian specimen. Therefore, we can say that the higher proportion of stronger shear microcracks in Brazilian specimen than in a specimen tested under the direct tensile load explains the difference between the tensile strength obtained from Brazilian test and those obtained from direct tensile test. And I want to explain this in another way. Most of you probably know this graph. Shows that typical failure modes of rocks in terms of more circles and more column envelope. The induced stress inside the Brazilian test, it resembles the confined tension failure modes, as represented here with this blue, sorry, this blue circle. In this case, there is a normal compressive over the microcracks, resulting in higher shear strength. As you can see, we can have normal at this section, compressive strength over the microcracks. This normal compressive results in higher shear strength values along microcracks. Therefore, we will have stronger microcracks. They need more energy, more work, more load to shear. And therefore, the presence of more shear microcracks with higher shear strength during the failure process of Brazilian specimen increase the overall tensile strength of specimen or the same material, like granite. In contrast, the stress state in the direct tensile test or direct tension under the direct tension is equivalent to the uniaxial tension, as we can see represented here with this red circle. In this case, when we apply the load, there is no, as you can see in this graph, we don't have any compressive load. The all load is tensile. Therefore, what does it mean? It means that it has a minor role of shear microcracks in overall failure and tensile strength of direct tension specimen. As you can see, the maximum shear strength here in this case, is much smaller than maximum shear strength is in this case. This is the Brazilian test. This is the uniaxial test. Therefore, we have more shear microcracks in Brazilian test, and each shear microcracks has more is stronger, need more energy, more load to failure. Therefore, this contribution of higher and stronger shear microcracks increase the overall tensile strength obtained from Brazilian test when we compare with those tensile strengths obtained from the tensile test. But up to here, we talk only about the material, rock granite material. We wanted to know if this conclusion, this we obtained our outcomes, is it correct about the other materials, the fiber material? Therefore, we had the same test on mortar materials. We did the Brazilian test on mortar. Here is the overview of the results of acoustic emission or microcrack types. As you can see, in Brazilian granite, we had majority as shear, okay, but here they decreased, the shear decreased to 27%, and the tensile microcracks increased. Again, that can simply explain why when we test different materials, we have different resistance. Here, just from this figure, we know that at the right side, we have higher number of shear microcracks. On the right side, we have less number of shear microcracks. Shear microcracks take more energy, more load to fail. Therefore, they contribute more in tensile strength. Therefore, between granite and mortar, we have higher tensile strength in granite because we have higher shear contribution. What about the tensile strength of mortar in direct tensile test? As you can see here, the majority of the microcracks are tensile, 94%. Of the acoustic emission detected or microcracks detected are tensile. Only 2 and 6% are non-tensile. What we had in Brazilian, in the granite specimen. In granite specimen, we had 55% tensile. Again, if you want to compare the tensile strength of mortar and granite, we know that the granite has a higher tensile strength. But how we can explain that? Simply by the contribution of shear microcrack. Actually, we know that we have other parameters, but if we just concentrate on this microcracking process, we can explain a part of this difference to the different contribution of shear microcracks. We have 22% shear, we have 2% shear. Then definitely we have higher tensile strength in granite than mortar. But very interesting result is that we obtain this ratio for both materials. The direct tensile strength to the Brazilian tensile strength for granite was 70%. And we had the same percentage, 70%, for when we compared the tensile strength obtained from Brazilian test, from direct test over the Brazilian test for mortar specimen. Therefore, we can conclude that this ratio is applies no matter what, regardless of the material, the type. And more interesting is that we did the same test procedure, monitoring, acoustic emission, and DIC for biomaterials. And what we obtained that the same, almost the same value, 0.7 for direct tensile test over Brazilian tensile test for biomaterials. Therefore, we can, with a high, with high certainty, we say that the tensile strength obtained from Brazilian test, from direct tensile test, is 70% of those obtained from Brazilian test. This is very important when we use in the tensile strength in laboratory in our design, because usually we get our tensile strength from laboratory from Brazilian test, and we cannot directly use those value in our design in numerical simulation or analytical calculation. We can say that if we use Brazilian tensile test, for example, in spalling prediction models, because the spalling is a pure fracturing mode. We may overestimate the rock's true tensile capacity, which could lead to unsafe support design. This unsafe support design could happen for slope stability also when we use the tensile strength obtained from Brazilian test directly to the model. And we were curious about, and this is the work that for the first time we've done. We wanted to know that if the different testing methodology, testing type, has any effect on the microfracture roughness, actually the roughness of the surface of the final fracture, microfracture. We studied that. Here is like the visualization of this morphology or surface morphology of the specimen under direct tensile test. Here, Brazilian test for granite and for mortar. From the first view, you can see that these direct tensile tests are a little rougher than these samples, Brazilian test. Why? If we wanted to characterize or quantify this roughness, we use the Z2 value. Z2 value is like a characteristic parameter to characterize or quantify the roughness surface of the fractures. The higher Z2, the rougher the surface. As you can see, in all cases, for mortar, indirect mortar, indirect granite, and biomaterial, we have a little rougher surface of the final fracture in Brazilian test than in direct tensile test than the Brazilian test. We have rougher fractures from direct tensile test than those from Brazilian test. But how we can explain this? And this is that rougher surface would be due to the higher contribution of tensile microcracks in direct tensile test. In contrast, those that we said that the higher contribution of shear microcracks increase the tensile strength. Here we say that higher contribution of tensile microcracks resulted in rougher surfaces. Why? Here, this you can see again, we have higher number of tensile microcracks, rougher surface for mortar. For mortar, we have higher tensile acoustic emission, tensile microcracks, and we have rougher surface. The same for granite. For biomaterial samples, we have higher number of tensile microcracks, we have rougher surface. And in the literature, in the other research, we have seen that tensile cracks is featured by many grain boundaries. Grain boundary cracks. It means that tensile cracks prefer to go through the boundary of grains, while a shear crack is associated with many transgranular cracks. Here is the microscopic thin section of the cracks on the shear on the tensile load. As you can see, shear cracks, because they have higher energy, they consume more energy, with more loads. They can pass through the grains directly. Therefore, they produce like this. They produce less or a smoother surface. On the other hand, because the tensile cracks has lower energy, and always the cracks or the fracture prefer to pass through the weakest zone, weakest bonds. And in granular materials, the bonds between the grains are the weakest bond. The tensile cracks prefer to go through the bonds, as you can see here. This is the tensile crack that pass through the grains. Therefore, here we can observe why we have rougher surfaces from direct tensile test and smoother surfaces from shear test in Brazilian test. Because in Brazilian test, we had higher number of shear microcracks that they sheared the surface. But in direct tensile test, we had higher contribution of tensile cracks that they pass through the grain boundaries. They produce a rougher final surface. If I want to review these, here we can say effect of microcrack mechanism on the tensile strength. Simply, we saw that higher shear microcracks resulted in higher tensile strength in Brazilian discs. We test the same material, yes, but the microcracking mechanism is not the same. They're different. Shear microcracks that are dominated in Brazilian tests. Shear microcracks need consume more energy to fail, to break. Therefore, they consume more work or load to get the final load, the final failure. That's why we obtain higher tensile strength in Brazilian tests. And effect of microcrack mechanism on roughness. As we saw here, rougher fracture surfaces correspond to the samplers with higher contribution of tensile microcracks. In other words, the microcracks and the fractures obtained from direct tensile tests has rougher surfaces. And as a conclusion, I repeat this, that tensile strength is mechanism dependent. It's not just a single inherent material properties. The microscopic failure strength of granite or mortar granite is controlled by the microscopic damage. And direct and Brazilian tests activate different macro mechanisms. As we see, direct tensile test is dominated by tensile microcracks, while Brazilian test had higher proportion of shear microcracks. Shear microcracks possess higher intrinsic resistance or strength, therefore, they contribute more in increasing the tensile strength of the same material in Brazilian test. And therefore, we can say that the difference between direct and indirect tensile strength values, both for intact and biomaterial specimen, was explained by the fact that in the Brazilian test, we saw more shear microcracks, which are stronger in nature than tensile microcracks. And the engineering takeaways or implications could be test selection matters. Using Brazilian tensile strength in tension-dominated field problems may overestimate true tensile capacity. Actually, we can use the Brazilian test to determine tensile strength of materials, but we need to make sure that where we going to use this tensile stress, if our stress state in the field is a biaxial or triaxial stress state, or is really a pure tensile or tensile stress state like spalling or rock burst condition. In spalling and rock burst in deep mining, we cannot use directly the Brazilian tensile strength. We need to reduce it to 70% according to my research and other researchers, to get the true tensile strength of materials. Therefore, the mechanism is very important. Field failure are often tensile driven. Spalling, excavation damage, slope cracking, and interface demanding are tension control. The tensile strength here plays a critical role. Design approaches should consider mechanism representing tensile properties. If we are able to track or use the acoustic emission or macroseismic monitoring during the field, we can determine the type of microcracks during the construction, for example. If we have when the crack initiate and where it initiate and the type of microcrack. If it's really tensile microcrack mostly in our next design, maybe it's better to use two tensile strength values, not the biaxial tensile. But if we have like shear dominated microcracking mechanism, if we determine from the field, we can use the Brazilian tensile strength directly. And the microcrack mechanism influence fracture roughness. With higher number of contribution of tensile microcracks produce rougher surfaces, and fracture morphology affects shear strength. After that, we have failure. If we can determine that the failure is based on the tensile failure, we can estimate the roughness. Actually, this step is the first step that I've never seen the other researchers. It's the first step we started to do. We have a long way to go, but if we can determine the correlation between shear strength and the percentage of microcrack, tensile microcracks, and the roughness, we can have an estimate of the shear stress after failure. And we can determine the hydraulic conductivity because the rougher surfaces decrease the hydraulic conductivity, and it controls the interface performance between rock and concrete models. And finally, reliable engineering design requires not only measuring strength or single value, but we need to understand the mechanism that produce this strength. It's very important. Thank you so much. If you have any question.
Excellent. Thank you very much, sir. This was great.
My pleasure.
Are there any questions online? You're welcome to ask your question on the chat or raise your hand and I'll give you access to your mic. Oh, hold on. Let me give you access. Oh, go ahead. Yeah, Yannick, are you able to unmute?
Yeah, you hear me?
Go ahead. Yes.
All right. So French or English?
Sure.
C'est correct, mais anglais, c'est parce que je pense que les autres personnes, c'est pas.
English. Okay,
Well,
so we're going English. Very good presentation, very interesting. I really appreciate your work, and it's really well presented. So it's really clear. And so congratulations for your presentation. My only question I have is about, I realized, but based on what you present in your slides, that the scatter or the variability of the result that you get from direct tensile tests is lower than from original tests, which for me was curious, because when we perform the same test for concrete, we get the opposite. So I was wondering why typically when you perform direct tests for a concrete cylinder, the variability is quite large in terms of tensile strength. But now in your test you get the opposite. So I was just wondering why we have this difference.
Actually, I've seen some very small report that say opposite, but the majority, I think, I would say 95% is the same. They have resilient tests higher than the tensile test. But in your case, maybe the testing configuration of or the material, have you done many tests or just a few tests that gave you?
No, actually, I'm basing my comment on literature review. Actually, once I had to do some literature regarding tensile strength of concrete, and then that's what I observed in the literature review. So it's an observation from my side. I didn't perform any tests, but I was just wondering why I found that. And in your case, you actually, well, that's what I observed. Maybe I'm wrong, but that's what I observed.
I don't have any answer for that because I haven't seen, for me, for most of the samples, all the samples that we've done, we arrived with a good consistency with the same results. And even when I showed you, let me. This graph that I showed you from the beginning, we can have sometimes reported that. So.
But I just want to be sure that the C, because in your presentation you use CV, so I guess it was yeah, I think it was CV. So I guess it was the coefficient of variation, or kind of
variation. Yeah, coefficient of variation. We had very small coefficient of variation, very small. When we had very good consistency in the results, because the thing is that we had very attention to the sample preparation with the time of curation, the time of testing, the duration of testing, the loading, all the sample surface to decrease the all uncertainties as much as possible. That's why we had very small coefficient of variation, and we done, I think, more than 100 tests and samples.
Okay.
But
Thank you.
here, my pleasure. Here you can see that this is the results of the rods. And as you can see, the majority of results, they say that the present tensile strength is higher than a direct tensile strength, because if we have the line of 1 by 1 is here, all the results fall beyond below the line 1 by 1, means that present tensile strength overestimate direct tensile strength. And I think in majority of tests the same result, but not about the concrete. About the mortar and about the rocks I've studied, but maybe the concrete is the stress constant. Well, there's a good subject to study. Maybe because the difference between grain sizes is stress concentration, or could be other answer.
Fine.
Thank you
Thank
for your
you.
question. My pleasure.
Are there any more questions from the audience? Excellent. Well, in any case, the presentation is recorded and will be made available on the CARMA webpage as well as the Rock Engineering Society's webpage. Thank you so much, Suren. This was greatly appreciated. For those online related to the rock mechanics groups, please note the CIM conference is coming. There will be a strong rock mechanics show and the AGM for the Rock Engineering Society. On the CGS side, we'll have Geo-Quebec this fall with a rock mechanics gathering and a bunch of sessions. And finally, for the local sections in Montreal, our next event will be on March 19th. You should see the invites coming in shortly. It will be a joint event with the Tunneling Association of Canada. Suren, merci beaucoup. Everybody here today, thank you so much. Have a pleasant weekend. Take care. Thank you.
Thank you. Thank you, everyone. Bye.
Yep. Goodbye.